4, we have several formulas here for example 3. They all mean the same thing. We've got y of t equals y sub 0 e to the kt. Some books write it as p of t equals p e to the rt, pert. Or some write it p of t equals p sub 0 e to the kt, poked. However you want to remember it is fine. This book is using the y's. And so example 3 says, the APY of a savings account is the percentage increase in the balance over a course of a year. Suppose you deposit $500 in a savings account that has an APY, that's a yearly yield of 6.18%. Assume the interest rate remains constant and that no additional deposits or withdrawals are made. How long will it take for the balance to reach $2,500? So that's what they're asking us to solve. Now, you got to be a little careful with this because in pre-calc we did something a little different where we just put the 6.18% in for K. But that really isn't what is happening. It's giving you an APR, which is an average percent yield. So what you're supposed to be doing is saying, well, we're going to let y sub 1, after the first year, it's going to be worth 1.0618 of the initial amount because it's going to gain 6.18% interest. So the 1 is the initial $500 and the 0.0618 is the interest. We also know that y of 1 is equal to y sub 0 e to the kt, and since t is 1, that would be a 1. Since both y sub 1s are equal to something different, we can set them equal to each other. So I'm going to write y sub 0 e to the k times 1 is just k. The y sub 0s are going to cancel. And then to get the k out of the exponent, we're going to put a natural log through both sides of the equation. The natural log and the e will cancel each other out. And then if you go to the calculator, I got k is approximately 0.060, which is a little different than the 6.18%. So it's going to give you a different equation. So this equation becomes y of t is equal to 500 initial amount e to the 0.060 t. Then the question was, when will it be worth 2,500? So we're taking 500 e to the 0.06 t equal to 2,500, divide by 500, and get 5. Put a natural log through, and then divide by the 0.06, and I got 26.8 years. That's how long it'll take. Now, I know sometimes you'll get the same answer using the other number, but the questions in the My Math Lab specifically ask you to get the growth rate, and if you just put in the 0.06 or the 6%, it's not going to be right. And now example 4. Example 4 is using total energy used, and the formula they've given us is total energy used is equal to the integral from a to b, the rate of the energy, dt, which is equal to a to b, p sub t, dt. And they've got a whole little derivation for you in the textbook. But example 4 says, at the beginning of 2006, the rate of energy consumption in the city of Denver was 7,000 megawatts. So we have a starting point. And we're going to start with our equation. P of t is equal to, and I'm going to write it as poked, and it says the rate was expected to increase at an annual growth rate of 2% per year. Find a function that gives the power or rate of energy consumption for all times after the beginning of 2006. So this is another one of those weird problems. So what we're going to do is we're going to write P sub 0, and we're going to go with one year's worth. P sub 0 e to the k times 1 would be equal to 1.02, that adds the 2%, of the initial amount. And this is part A we're working on. Because we're dealing with a 2%, which is 0.02, so I need 1.02 to put in there. And then if I solve that, p sub zeros cancel, put a natural log through, and I get the natural log of 1.02, which gives me 0.0198. So the equation I'm dealing with, this is the question they were asking for, was the function. 7,000 was the initial, e to the 0.0198 t, where t is greater than or equal to 0. Okay, and we were starting this with 2006. So part B wants to know, find the total amount of energy used during 2010. Well, if 2006 is times 0, 2010 is going to be the interval from 4 to 5. So they are asking us to integrate from 4 to 5 the function. Okay, so I'm integrating e to the junk, which is just e to the junk, but the junk's derivative is 0.0198, so I've got to make sure I put that in front. So I've got the 7,000 that I'm leaving there, 0.0198 in front, e to the 0.0198t, and evaluate it from 4 to 5. And if you plug and chug your way through that, the book says you get 7,652, and these are megawatts per year. Uh-oh, there. Actually, megawatts dash year. Yeah. Okay, then part C. Part C says, find the function that gives the total cumulative amount of energy used by the city between 2006 and any time t greater than or equal to 0. So part C. Okay, so they want us E of t, energy, is going to be equal to, you've got to start with your initial energy, plus you're going to add to it the E prime of t dt from 0 to any time t, which then turns into E of 0 plus the integral from 0 to t of P of t, which then turns into 0 plus the integral 0 to t of 7,000 e to the 0.0198. Oh, now I guess I should be using s's, not t's. I guess it doesn't make a difference. I can use whatever letter I want. T dt. So you integrate that and you get 7,000 over 0.0198 e to the 0.0198. I see what I want to do. I want to change my variable out. Let me fix this. Let's use an S here. The book used an S, and it'll be easier on your brain when you're looking at the book. Because now that I'm going to plug and chug, it's going to look weird. So S is going here. S, ds from 0 to t. Otherwise, I'm replacing t's into t's. So then this turns into, and they rounded this, 353, 535 e to the 0.0198 t minus, now if I stick 0 in there for s, I get e to the 0, which is 1. So minus 353,535 times 1, which is comma in the wrong place. And so we could factor that all out. 353, 535, parentheses, e to the 0.0198t minus 1. Looks a little simpler. And that's the end of number 4.